So now we are gonna talk about edge coloring. So there are certain problems that we want to, be more concerned about the pairwise relationship between objects rather than the type of objects. For example, assume there are some people, and some pairs of the peoples must have some meeting. So this person has to have a meeting with this person, 3 times. And this person has to have a meeting with 2 people. Right? Somehow, so this person has to have a meeting with 2 people. And now we are concerned about this pairwise relation. So these 2 people have to have a meeting, but these 2 does not have to. And we want to schedule a meeting. So there are several time slots, and we want to schedule it. And while doing that, if this meeting has to be happening at 10 a.m., then this cannot happen at the same time. You have one body, so you cannot attend 2 different meetings at the same time. So in that case, we assign time slot for each this pair, and then those time slots can be represented using colors. You want to assign the color so that the 2 incident edges gets different color. So this is one example that we want to consider the coloring on edges. There are many other situations that this can be useful. So we say K edge coloring of a graph is a labeling of its edges from a set of K colors. Again, we usually use the bracket K, the set of all integers from 1 to K as the colors, but in theory it could be anything. And we say that it is a proper coloring if any incident edges receive distinct color. And we say that a graph is K edge colorable if it has a proper K edge coloring. And we define the edge chromatic number. Or sometimes we call it chromatic index. And then we write chi prime of G. Again, chi is the chromatic number, and then when you add the prime, it's parameter related to edges, edge version of this parameter. So this is the minimal K such that G is K edge colorable. So now we introduce new parameter I prime, and we want to explore the relationship between this and the previously known concepts. One of the things is that one easy observation is that this chromatic index, H chromatic number, is same as the chromatic number of the line graph. We call that this line graph of G is the graph with the vertex set as the edge set of G. And then E is the E prime where they share a vertex. So if we vertex color this graph, and those vertices are actually the axis in the original graph G, so it's pretty obvious that these two are the same concept. Okay, and now we want to apply the most basic algorithm, the greedy coloring algorithm. Yeah, on one more note is that when we consider KH coloring, it makes sense to consider multigraph in some cases. So what I mean is that there are differences between simple graph and multigraph. For vertex coloring, having multiple edges means nothing. You are only considering about the vertex coloring, and then having one edge between them or two edges between them makes no difference. But for edge coloring, if there are two edges between two vertices, that you have to give them different colors. So considering graph and multigraph makes difference. Okay, so if you apply greedy algorithm, greedy coloring on, say, multigraph, then what do we get? We easily get this inequality. Why? If you have a maximum degree at most delta, if you take one edge, then how many edges are incident with it? At this vertex, there are delta. This is multigraph. Possibly delta edges are adjacent, incident with this vertex. Then, except this one that we have chosen, there are delta minus one of them. And here again, you have one vertex, then there could be at most like this one again. Delta minus one edges other than this, which are incident with this vertex. So together, there are two delta minus two. And then this is the maximum degree of the line graph. This is at most two delta minus two. So using the trivial bound, you add one to get this upper bound. So you have this. And if we further use the Brooks theorem, then as long as this is not complete graph or all cycle, this line graph is not complete graph or all cycle, then we can improve this one more. Okay, but that's using some structural information about this graph to improve this upper bound, right? But this graph, this line graph, is not just any graph. Of course, when we improve this using Brooks theorem, we use the fact that this is none of those two graphs. But furthermore, it has furthermore more structure. For example, one of the special property of this is that if you have it doesn't contain this. If it's a K13, no K13 at induced subgraph. So LG has no this such structure. That means if you have one vertex and then three neighbors, at least one edge should be there among these three vertices. Why? I mean, that's pretty, easy to check. So this vertex is actually an edge in original graph G. And this one is also an edge in the original graph. And, this vertex, this one. And then since they are adjacent, it could be either here or here, but let's say on the left side. And then this one is also there. But if you want to make sure that there are no edges between these two, this one has to be adjacent, incident with this vertex. For the third one, it's either going to this way or this way. But in either way, either that edge is here, that edge is here. So it doesn't contain this as any subgroup. So this shows that this is not any graph. This has certain structure. So we might wondering that using that structural information, can we further improve this? So question is that a better bound. Can you obtain a better bound? Okay, when we want to find a better upper bound, we want to first find the good lower bound example. If we want to find the optimal upper bound, then finding some good example which give you some worst case lower bound, then they might give you some idea. So since we are considering multigraph, one of the possible example is this fat triangle. Let's say delta is even. Here delta over too many edges between these two vertices. And every vertex has maximum degree delta, maximum degree delta, maximum degree delta. Okay, now what? Every edge must have a different color. So this shows that the chromatic number of this graph is at least half 3/2 times delta of G. In fact, this is equality because, you give the every edge different color and this holds. So this is the, best we can hope for. Best upper bound we can hope for. Because of this example. Indeed, Shannon proved that this is true. And Beijing and Gupta proved this. Here, what's mu of G? The mu of G is the largest edge multiplicity in G, where what edge multiplicity is, we define edge multiplicity of UB is the number of edges between two vertices U and V. What do you know? This shows that if G is a graph, which means that if G is simple, then its chromatic number is at most delta plus 1. This is called Beijing theorem. Okay, this is upper bound for simple graph, and for multigraph we have this more general upper bound. And what's lower bound? We have a simple lower bound that This is true. Why? Because if you have a vertex with maximum degree, all the edges incident with it, they are pairwise incident. They must have all different color. So this holds. In fact, you can write it in this way as well. So Kring number in this line graph is at least the maximum degree of G. Okay. So we have simple, based on these two, we have only two cases. Its S-chromatic number is either delta or delta plus 1. This is much simpler than the chromatic number case. Chromatic number could be anything between one and the maximum degree. Actually, 2 and maximum degree plus 1. But here you have only two cases. It's either maximum degree or maximum degree plus 1. We said that a graph is class 1 if it is delta of G at color. And it is class 2 if it is not delta of G at color. So you require one more color. And okay, let's define other terminology. We say that if we consider decomposition, which is H partition of a multigraph into perfect matching, is called one factorization. So you decompose it into one factor. And if a graph has one factorization, we say that, let's say if multigraph it is one factor. So once you add the color, then you consider the color graph. So what's color graph? Color graph is a set of edges consists with the same color, and they are matching. Okay, so edge coloring is same as the composition of the edges into matching. In fact, if all of them are perfect matching, then we say that this is the one factorization. Okay, let's consider some example. Maybe a before example. So, and this one factorization, with this definition, if we know that a regular graph is class 1 if and only if it is one factorable. So if you have a regular graph, if it can be colored with R color when it is R regular graph, then every vertex is adjacent to it, all R colors. So each color graph give you not only a matching, but also perfect matching. So it is one factorization. Then what? If we have a regular graph on odd number of vertices, then it doesn't have a perfect matching, so it is not one factorable. So we know that this is class 2, not class 1. So this is class 2, because it's not one factorable. And other example, if you consider the complete graph on 2n vertices, the even number of vertices, it's easy to check this is class 1. And say d-dimensional hypercube. QD, which is you take a 0, 1 sequence. So this is your vertex set. And these two are adjacent if only one zit is different. So this defines this d-dimensional hypercube. So this is 1-dimensional hypercube, 2-dimensional hypercube, 3-dimensional hypercube, and so on. So this is class 1. It's easy to check that you take one less dimensional hypercube and then matching between them. So you color all this matching with one color. And then, the other perfect matching, you can iteratively color them. Then you can actually color it with the delta color, D color, and then the maximum degree is simply D. Okay. So another possible example is that this is a graph called Peterson graph. And this is, you can check that this is class 2. Meaning that you cannot color the edges with 3 color. You need at least 4 colors. And by using the theorems that we proved in the section of matching, we can actually show that every bipartite multigraph G is class 1, delta H colorable. How do you do it? You take the XY bigraph, XY bipartite graph G, and let delta be its maximum degree. So you have X and then Y. What do we want to use? We want to use the fact that we proved that every bipartite multigraph, which is regular, has a perfect matching. If you have a regular bipartite graph, if you have a perfect matching, and you can delete those perfect matching, then remaining one is again regular bipartite multigraph. You can take another perfect matching, another perfect matching. So it's one factorable. So for those graphs, it is class 1. It's easy to show that. But if your multigraph is not regular, then what do you do? You actually want to regularize. What we do, we add the artificial vertices to the smaller part until both have the same size. So you add vertices to make them same size. We then add edges in an arbitrary way which joins vertices of x and y with degree less than delta until all vertices have degree delta. I mean, here we consider the multigraph. Multi-edges may arise in this process. It's easy to check that this is possible. I mean, if this is not delta regular, then there must be two vertices with a low degree, one in x, one in y. You add an edge. Even if there are already edges between them, we add another edge because we are allowing multigraph. Then at the end, we obtain a delta regular graph. As we have a delta regular supergraph H of G, meaning that the G is a subgraph of H, and H is also bipartite. Then we know that as we know, any regular bipartite multigraph as one vector. So H as one vector. I keep taking one vector, we obtain one factorization of H as G is delta colorable. So H is supergraph of G. If G has edge coloring, it naturally, reduced to the edge coloring of G. And then it uses most delta color. Okay. So this is one interesting case of graphs in class 1. So we know that every graph G is either class 1 or class 2. So there is only two options. But deciding which one is actually a difficult problem. Deciding graph, whether a graph is in class 1 or 2 is a difficult problem. So this is NP-complete problem. This is as complete as difficult as NP problem. All NP problem. So I'm not gonna talk much more about what this means. This is another topic, and quite frankly, I don't have a very deep knowledge about this topic of like P, NP, and anyway, so we will not talk about that, but this just means that this is a typical problem. Okay, and maybe let me introduce more generalization of the Beijing theorem. As I mentioned, Beijing and Gupta proved this for the multigraph, but later, Ore noticed that we can improve this. So here, this is the largest maximum multiplicity, and here the maximum degree. For all we know, maximum degree happens at this vertex B. Great. Somehow, the sync between the computer and my iPad is a bit slow. So when I already load something on my iPad, but it didn't show up in my computer. So now it shows up, okay. So this might be, okay, give me a moment. So let me, okay, so okay, now the sync is back. So this maximum degree might happen here, while the largest edge multiplicity may happen somewhere else. And Ora noticed that in this case, we can actually improve this. So he noticed that this edge chromatic number is as large as this only when this largest edge multiplicity happens at the pair which includes this maximum degree vortex. So writing that that mu xy is the edge multiplicity of the number of edges between x and y in multigraph. The owner proved that this edge chromatic number is at most maximum out of all vertices, where let's write that mu v at the maximum out of all u in neighbor of p, you consider the largest edge multiplicity, meaning that at this vertex, you consider all edge multiplicity. This one is the largest, so you keep mu of p as 3 here. Then this is maximum out of the degree of b plus b, the multiplicity of b. And yeah, there are several more generalization, and then probably the most general one is by Anderson in 77 and Goldberg 77 and 84, showing that for a loopless multigraph C, okay, so maybe I forgot to mention that in all these multigraph that we consider, we assume that there are no loops. If in terms of edge coloring, if there is loops, then I mean it doesn't really make sense. The edge is incident with itself. Oh no, okay. What am I saying? Oh, that was not correct. Okay, so just forget what I just said. So yeah, there could be a loop. In that case, I mean, as long as this loop gets different colored with the other edges, it's okay. Anyway, so this theorem is regarding only loopless Wolfsky graph. The edge chromatic number satisfy that the edge chromatic number of G is at most the maximum of the maximum degree and maximum out of all x, y, g, which are say in P, which means it's a 3-edge path. So x, y, g is 3 vertex path. X, y is adjacent, y, g is adjacent. So you take the degree give me a moment. Yeah. Degree of x plus degree of g, and then add the multiplicity between x, y, and then y, g, where p is the set of 3 vertex has in G. So they prove this, and this implies the previous theorems that I mentioned. Okay, we are not going to prove this theorem, so I just introduced this theorem to you. And we will prove the Beijing theorem says that for graph G, its edge chromatic number is at most maximum degree plus 1. So we will prove this in the next video.